Hello all, welcome to the next lecture of microwave engineering. So in the previous lectures, we have studied the propagation of transverse electric wave and transverse magnetic wave in a planar waveguide. So we have calculated the expressions for various field components in case of both TE and TM waves. Also, we have seen the characteristics of TE waves and TM waves. Right now, let us go to the next topic. So, in this topic, we will be studying about transverse electromagnetic wave, or also called as TEM wave. Transverse electromagnetic wave. Right. So, So this transverse electromagnetic wave is a wave in which both the electric field and magnetic field both are transverse in nature. That means both of them will have only transverse components, right? And the longitudinal components of both magnetic field and the electric field will be zero. Okay, so right, a wave in which both electric and magnetic field have only transverse components, right, and no longitudinal components. Only transverse components are present, no longitudinal components are present. Okay, that means the electric field and the magnetic field is completely transverse in nature. Okay, so that means that the longitudinal component of electric field Ez and the longitudinal component of the magnetic field Hz will be zero. Okay, Hz will be zero. Okay, so this kind of wave, this special kind of wave where both, right, the longitudinal component of electric field Ez and the longitudinal component of the magnetic field Hz becoming zero is called as a transverse electromagnetic wave, as in this case both electric field and magnetic field will be transverse to the direction of the direction propagation. Okay, so at any point, right, both electric field and magnetic field will be transverse to the wave propagation. Okay, so this kind of mode of propagation or this kind of wave is called as transverse electromagnetic wave. It is a special wave, right? TEM wave. Okay, so here, right, if I assume, so here, right, what happens is, so if the because the wave propagation is along z, right, okay, so the electric field will be only either along x or only along y, and similarly magnetic field will be either only along y or x. So right, there will be ex hy or ey hx. One of them will be, one combination will be present. Okay, so not all combinations can be present, right? So that is right. Okay, that is so. Here, the wave that we get is a uniform plane wave. So it is propagating in a single plane. Okay, so therefore the wave, the general electromagnetic wave that you generated outside the waveguide, when you launch it into the waveguide, into the waveguide, such a way that we get this TEM wave, TEM mode, the wave becomes a uniform plane wave and the wave becomes lossless. Okay, or the media becomes lossless and it acts as a free space. Okay, so this is the case, right? Right. Now, when do I get this TEM wave, right? So when do I get this TEM wave? Actually, this TEM wave is just a special case of transverse magnetic wave. Okay, it is just a special case of transverse magnetic wave, and we will get, okay, or we will right, convert the transverse magnetic wave into TEM wave by making, or by making the order of the wave as zero. Okay, so whenever the order of the TM wave becomes equal to zero, then the wave that is generated is called as transverse electric wave. Okay, so transverse electromagnetic wave, TEM wave. Okay, so TEM wave is also nothing but TM0 wave. Okay, it's also nothing but a TM0 wave. Okay, right. So we know when we will get TM waves. So TM waves will be generated, right, whenever TM waves will be generated whenever I launch what? I launch a parallelly polarized or horizontally polarized wave into the waveguide, right? Horizontally polarized or parallelly polarized wave, whenever we launch it into the waveguide, we will get this TM wave. Okay, but here the thing is, we should get m equal to 0 and we should make the more propagation possible. Okay, So that will happen when, right? So yesterday we discussed, in the previous lecture we discussed that the launching angle for any waveguide can be given as cos theta is equal to m lambda by 2d. Okay, so from this, if I want to get m is equal to 0, that implies, right? If I want to get m equal to 0, that implies my theta should be equal to 90 degrees. So whenever my theta is equal to 90 degrees, I will get m equal to 0. That means, okay, I will get a TM0 propagation, right? Isn't it? So, right? So whenever there is a parallelly polarized wave, right? Whenever there is a parallelly polarized wave or horizontally polarized wave, so for this wave, TM0 mode will be generated whenever we launch it with an angle of 90 degrees. Okay, so if I want to get, for getting m equal to 0, my theta should be 90 degrees. Okay, so therefore what we can conclude is we can get a TEM wave. So we can get a TEM wave inside the waveguide whenever I launch, right, a electromagnetic wave of parallel polarization, when electromagnetic wave, EM wave of parallel polarization, right, with an angle of 90 degrees. Okay, so with the launching angle of theta equal to 90 degrees. So whenever I do this, right, inside this waveguide, okay, I will get a TEM wave. Okay, I will get a TEM wave, right? TEM wave. Okay. Also, right, this will give us the TEM wave, right? Also, okay, for the TEM wave, right, one important point is, so if this TEM wave has to exist inside or is to propagate inside the structure, then the h value, the constant that we considered, h square is equal to gamma square plus omega square mu epsilon, right? So this h value should be 0. If the value of h is not equal to 0, then the waveguide will not propagate this TEM wave. Even though TEM wave is supported or generated inside, okay, it is the mode is getting generated, but it does not get propagated whenever h is not equal to 0. Okay, so we have to make sure our h is equal to 0. So, right, this is the right way of generating a TEM wave. Okay, so I can launch or I can get my TEM wave inside a waveguide whenever, right, I launch, okay, an electromagnetic wave of parallel polarization with a launching angle of theta equal to normal 90 degrees or normal incidence. Okay, whenever I incident the wave normally, right, if this is the case, so I have to incident my wave normally like this. So whenever I do this normal incidence, then inside the waveguide I will get a TE wave, transverse electromagnetic wave. Okay, right. Now, so this all things we have done. Right. Now, what are the field equations for the TEM wave? So as I said, this TEM wave is nothing but a special case of TM wave. Right. So for TM wave, we know that we have the components. The field components are given by Hy, Ex, and Ez. Okay. So right, Ez we write it as C1 into, okay, cos C1 into sine m pi by d into x, okay, sine m pi by x d, right? Ex is equal to c1 into gamma by h square minus gamma by h square into m pi by d into, right, cos of m pi x m pi d by x. And similarly hy is equal to c2, sorry, this is all c2 into, right, j omega mu by h square into m pi by d, okay, into sine of m pi by d into x. Okay, so these are the field expressions that we have derived in the previous lecture for the transverse magnetic mode. So you can go back and look at that video. So these are the field structures. Now if I substitute m equal to 0, so when I will get TM wave will be obtained whenever m is equal to 0 for the TM case. So if I substitute that, okay, so I will observe that Ez will be becoming 0 because, right, sine of m pi x by d. So when m is equal to 0, Ez will become straight away 0, right? Hy will not become 0, and similarly Ex becomes or might not become 0. It depends upon the h value, small h value. If small h is equal to 0, then Ex will not be equal to 0. Okay, so this is most important point, right? If this value Ex becomes 0, right, then there is no electric field component, so the wave cannot exist, isn't it? So, right, the TEM case will be valid only when small h is equal to 0. If small h is equal to 0, then Ex will not become 0. So we can verify that by putting m value in the above equations, and we can verify. So we will get these things. Okay. So therefore, for a TEM wave, right, Ez will be 0, Hz will be 0. That's what I said. Both the longitudinal components are always equal to 0, right? Only Hy and Ex terms will exist. Okay. So the wave will be like this. Okay. The wave propagation is along z-axis, right? So electric field will have its component along x-axis, and magnetic field will have its component along y-axis. Okay. So this is how the wave propagates inside the right waveguide. Okay. So these are the field equations, field expressions. We don't need to calculate what is the value of Hy and Ex. We just need to, because TEM wave is very difficult to achieve, and it is not practically possible. So right, Hy and Ex only they will exist. We have to show that they only existing. Okay, right. So this is the thing, right? Now coming to the special characteristics. Coming to the characteristics of this TEM waves. Okay, yeah. So till now we have seen, right, what is a TEM wave? TEM wave means transverse electric and magnetic wave. So both electric field and magnetic field will be transverse to the wave propagation. That is a point one. Second point, when I will get TEM wave will be obtained whenever I use parallel polarized EM wave, and I launch it with an angle of theta equal to 90 degrees. Okay, if I launch the wave with an angle of theta equal to 90 degrees, I will get the wave. Okay, next, right, what are the field expressions? So here Ez will be 0, right? Hy and Ex will exist. Okay, only Hy and Ex will exist. So the wave looks like a uniform plane wave. Okay, so right, all wave propagation, electric field and magnetic field are mutually perpendicular to each other. Okay, that's what we discussed till now. Now, what are the characteristics of the TEM wave? Characteristics of TEM wave. Okay, so first thing is, as I told you, so H is equal to 0. So TEM wave will exist only when H is equal to 0. Okay, so why is this? We will discuss in rectangular waveguides in more detail. So, right, when H is equal to 0, then only TEM wave exists. So H equal to 0 means, right, we know that H square is equal to gamma square plus omega square mu epsilon. This is equal to 0. So gamma square is equal to minus omega square mu epsilon, or gamma is equal to j into omega root of mu epsilon. Okay. So gamma value is, right, is equal to j into omega into root of mu epsilon. So from this equation it is very clear that, okay, from this equation it is very clear that irrespective of the frequency, whatever may be the frequency, right, my gamma will be always purely imaginary, right, isn't it? So gamma value will be purely imaginary, right? Okay, irrespective of whatever may be the frequency. That means, right, always my attenuation constant alpha will be equal to 0 for this case. Okay, right, only beta exists, right? So, right, there will be no attenuation offered by the waveguide for any frequency. Okay, so for any frequency, there will be the attenuation offered by the waveguide is always equal to 0. Okay, so that is why, right, this TEM mode of propagation can propagate all the frequencies. There is no lower limit, or there is no cutoff frequency or minimum frequencies. All frequencies get passed. Okay, all frequencies get passed through the waveguide. Okay, so there is no cutoff, or there is no minimum frequency. Every frequency gets passed through the waveguide. Such a kind of every frequency gets passed through the waveguide. So that is the special feature of the transverse electromagnetic mode. Okay, right? Point one. Okay, so there is no cutoff frequency for this mode, right? Every frequency will get passed because gamma is always right. Gamma is always purely imaginary, irrespective of whatever the frequency is. Okay, right? And as I said, similarly, alpha will be 0 and beta only exists, and beta is a real value. Okay, some constant value. Right. This is a point 1. The point 2 here, the special feature is, okay, so cutoff frequency, there is no cutoff frequency for the transverse electromagnetic wave. Every frequency gets passed through it. Okay, right. Second point is, right, okay, cutoff frequency is 0. That's what we say. Cutoff frequency or minimum frequency is 0. There is no cutoff point. Second point is, right, if I calculate the velocity, which we will see later, okay. So here, right, the wavelength or the frequency of the wave, right, is not depending upon the mode, okay. There is no component of mode here, right, m value. So always, right, for any mode, okay, the wave, the frequency or the velocity of the wave will be right same. So therefore, this TEM wave is non-dispersive mode. It is a non-dispersive mode. So there is no dispersion of wave. What is this? We will discuss when we get into the calculation of velocity. Okay, no dispersion. So no dispersion, right? No change of these things. Okay, right. And the third is, right, as we discussed, the TEM mode, right, for the TEM mode, the waveguide acts as a free space, okay. So it acts as a free space, right. So the velocity of propagation, in this case will be equal to the free space velocity. So the velocity at which the TEM wave travels is equal to the velocity of light. Okay, so it is equal to the velocity of light, and the free space characteristics hold good for this TEM mode propagation. Okay, right. So these are the important characteristic features of the transverse electromagnetic mode. Right. This mode is very difficult to achieve and practically almost impossible to obtain in any waveguide. Okay, so right, but theoretically when it exists, right, and this mode will be obtained whenever the mode order m equal to 0 for a transverse magnetic wave. That is when we launch a transverse magnetic wave with normal incidence, that is by making an angle of theta equal to 90 degrees. Okay, so whenever we do this, we get a transverse electromagnetic wave. Okay, so this is a special mode that exists in the planar waveguide, right? So I think this is clear, right? So in the next lecture, we will continue with the special characteristic features of the waveguides, such as attenuation, wave impedance, and wave velocities, phase and group velocities. Okay.